Now, I'm not advancing the slides. I'm on share. Maybe I have to do it with that. Okay, all right, I'm going to click and have a bit of a problem there. Okay, that's good. Okay, so I'm going to start off with, as is Cambridge, with pulsars and Pulsars, of course, as you know, were discovered here and recognized to be rotating magnetized neutron stars. Is there a pointer or something? You got a pointer? Oh, here we go. Oh, manual one. That's good. Okay. There's not a laser at the end of this. Okay. Fritz Zwicky, Robert Oppenheimer, who, well, I think everybody knows what they contributed, and Franco Boccini there, who predicted that the Crab Nebula over here might have a spinning magnetized neutron star in it. Fred Hoyle actually said something similar, but nowhere near as developed as Franco. And then the discovery was made by Jocelyn Bell and Tony Hewish. And I would like to say a word about Tony, who passed away a month ago. And it was a truly great discovery that Jocelyn and Tony made here at the Hopfield, and one that sort of changed astronomy completely. Here's the so-called little bit of scruff, the original sort of detection. And I have a sort of memory myself of being here as a first-year undergraduate, attending I belong to the Astronomy Society in the university, and Tony gave I think one of his first lectures actually to the Cambridge Astronomy Society on the pulsars, and he was very fulsome. I can even recall at this time, very fulsome in explaining how Jocelyn had made this sort of great discovery using the Hopfield. So that was for me, it's a sort of nice to be back here at this time. As you know, the identification very quickly of pulsars with neutron stars happened. People thought they were spinning, pulsing white dwarfs and so on, and then that became unclear. And then there was a connection, of course, back to supernovae through Barden and Zwicky, but also Shklovsky made the connection back to X-ray astronomy. And one of the very first X-ray sources discovered in 1962 was SCO X1, and was recognized as proposed to be a neutron star about that time. So that's sort of neutron stars, and sort of giving a fairly general introduction. Here, the neutron stars, just to refresh people's memory, as I know there are people here with different backgrounds listening to this talk. The regular neutron stars, about 10 to the 57 nucleons, which means their radii is about 10 to the 19 Fermi, about 10 kilometers, and they're mildly relativistic objects, inevitably. And the magnetic fields on them are 100 megateslas. I'm going to use SI units. I recall that again, I think as a first or second year student here, I listened to wonderful lectures by Sidney Kenderdine on electromagnetic theory, which contained one serious mistake. He said, I'm going to teach you SI units because in a couple of years, everyone else will be using these. So that hasn't actually happened, but I had to make a choice, and so I'll go into SI units. This, of course, is about 3 trillion times the magnetic field on the Earth for a regular pulsar. Here is, as you know, between 1/2 millisecond and 30 seconds. They're also gamma ray pulsars, and they store a lot of rotational energy. And the emission that we see from them, which is mostly, of course, in the gamma rays, not in the radio, mostly in the gamma rays, comes basically from the rotation extracted by electromagnetic torques and current cars. We'll have a bit more to say about that. The radio astronomers have a convention of thinking about these objects in terms of brightness temperature, so what the intensity expressed in terms of sort of radio temperature, and they would be up to about 10 to the 30 degrees Kelvin. So that's what the radio astronomers often discuss, the emission from pulsars. And as you know, they're spinning magnetized neutron stars with the magnetic axis, the spin axis, and then the neutron stars themselves are a physicist's playground, a laboratory. You see matter under extreme conditions and lots of physical phenomena you find nowhere else in the universe, and nowhere else, certainly not in the laboratory. And this is the this is, of course, is a lot that one learns from pulsars, seeing them not so much as emitters in their own right, but as tools for probes of both cosmology and of the nuclear physics and condensed matter physics and so on associated with neutron stars. So those are sort of the regular neutron stars. And a question that I will raise that arose early on was not how do they pulse, that was obvious, they spun, but how do they shine? And this is the way John Ayres is famous for saying this, how do pulsars shine? And they shine, and there were various mechanisms that were proposed. In fact, there was Martin Rees is here in the audience with Franco Pacini, I think I just showed, and Peter Goldreich, I think it was in about 1969, wrote a quite, it was a very sort of succinct summary of the options that are available. And the one of them is a sort of antenna mechanism where you imagine instead of, if you want to have a very high brightness come out, you've got to have a lot of kinetic energy, the emitting particle, if you like. So you could imagine a large bunch of electrons or positrons streaming along a magnetic field, behaving like an electron moving on a curved trajectory, called curvature radiation. And that's a good idea. It has a problem when you look at it in detail, because if you imagine being on a running track and you have to run around the outside of the track rather than the inside of the track, and you've got to travel almost at the speed of light, it's very hard to keep up on the outside of the track. And so there really is a kinematic problem with this mechanism, but it's possible. The second class of mechanisms, which I identified then, was the sort of maser mechanisms. And here you have beams of particles. Typically you have, not always, but typically you have a beam of particles that would create an inverted distribution, population inversion, if you like, and you can get traveling waves that grow exponentially. I'm not going to go into any of the details of any of these mechanisms. I'm just trying to give a sort of overview of the picture of what's going on. And then there's a third type of mechanism which has been discussed, more so in recent years actually, but I think many of us are interested in the past, and that was wind mechanisms, which was that the emission actually comes way beyond the light cylinder in the electromagnetic wind that leaves the pulsar, and their current sheets can produce coherent radio emission of very high brightness temperature. And so I'm saying this now because this is going to come back when we talked about fast radio bursts. So here, I now like to go on to the next part of this, which is magnetars. And these are magnetic fields, these are neutron stars, excuse me, with magnetic fields that can be up to 1,000 times more than that in a traditional neutron star associated with a pulsar. So they go up to about 100 gigateslas in magnetic field, which is now 3 trillion times that on the Earth. And for the physics reference, we often talk about a critical or a Schwinger field, which is where the quantum of energy associated with alarm or gyration in the magnetic field is equal to mc squared, and this is going to be 30 times that quantum electrodynamical field in the fields that are this strong on the surface of the neutron star. And these, the idea that there might be neutron stars with magnetic field this large was a sort of imaginative leap made by Chris Thompson, the only photograph I could find of him, and Rob Duncan, and it was largely vindicated by another colleague of mine, Chris Kavli, who actually found that the identification of so-called soft gamma repeaters with these highly magnetized neutron stars was indeed likely to be the case, and the evidence of that has got stronger and stronger over the years. So these class of objects that are neutron stars, we're not sure about their provenance, but I think a good guess, which probably most people sign up to, is that they're probably ages up to centuries, not much more, but they're very young objects, very hot objects. What fraction of newly formed neutron stars and supernova remnants are become magnetars is unclear, I think, but could be as many as 10% of core collapse supernovae leave you with these strongly magnetized magnetars. These objects are very important. They're very different from the regular neutron stars because the magnetic energy that they contain is about 10 to the 41 joules, and it is the source of the power for the emission that's seen. They're typically rather slowly rotating because they very quickly slow down, periods of about 5 to 10 seconds or so, and 10 seconds. And so it's really the magnetic energy that is the source of the power for the emission that is seen from magnetars. So having introduced those magnetars, let's go on to a little bit to the observations. And now introduce, it seems like I'm rambling around, but there is a connection here. These are the gamma ray bursts. These, of course, were discovered in the late 1960s by satellites looking for nuclear tests and so on, and they realized that they were cosmic objects. And we now know that there are primarily three basic and very physically different types of gamma ray burst out there. They're the soft gamma repeaters, which along with the anomalous X-ray pulsars were identified with magnetars typically, and some of them are also radio pulsars, I should say. And then in addition, there are long gamma ray bursts, so-called long gamma ray bursts, which had characteristic emission timescales more than about 2 seconds. And these are associated with core collapse supernovae and probably black hole formation, although none of that is absolutely secure yet. And then there's the short gamma ray bursts with durations typically less than about 2 seconds. And these are associated with something very different, neutron star mergers. And this has been sort of vindicated, if you like, by the gravitational wave object 0817. But it's not clear that all of them are of this type, but it's certainly looking like a better and better bet. And you're left almost certainly with a spitting black hole, though in principle you could be left with a very heavy neutron star. So they're very different types of objects. The point I want to make here that is going to come back is that this so-called generic class of astronomical objects, gamma ray bursts, like the supernovae, really comprise physically very different mechanisms. And we'll come back to that point in a moment. Okay. So now I'll talk about, having done GRB, I'll do FRB. I'm not sure what the next big discovery in this business is going to be, but I'm going to predict that it's going to be called an ERB for short. And so, but at any rate, the fast radio bursts were first discovered in old data by Duncan Lorimer and his student Narkovich, who I've never met. Something like a reprise of Jocelyn Bell and Tony Hewish, and they found this in 2007. And there was a lot of confusion about this because radio astronomers have been finding bursts in radio data for as long as you want. And of course, a lot of it was thought to be interference and so on. A lot of it, what they had seen was interference. The most embarrassing part of all, well, we'll come to what was the embarrassing part in a moment, but typically they're now known to be a real phenomenon, and you can pick the signal from the noise, and they're observed typically from about 300 megahertz to 8 gigahertz. They're radio objects, just radio objects, brightness temperatures now up to about 10 to the 35 degrees Kelvin. And from a physics perspective, I'll make this point again, is that if we think about this in terms of the occupancy of a state, which is the physics way of thinking about it, we give it an occupancy, call it N, if you want, that'll be about 10 to the 40. Okay, so it's a good job these are bosons. All right, so they're not so another way of saying this is these are intensely classical emission, and it's the same occupancy as every astronomer should know at the source and at the telescope. It's the same intensity and so on. They're highly polarized, both linear and in some cases circular, sometimes up to about 100%. Typical durations of these bursts after you removed the effects of propagation, which I'll come to in a moment, the typical duration of these bursts are about a millisecond, but they can have structure on the 10 microsecond scales. And there may be structure on shorter scales too, and some of them obviously go on for much longer. They're a highly heterogeneous class of objects. They, one phenomenon that has caught the attention of the observers and the theorists, and indeed the journalists, is a common but not universal pattern of having the emission decrease in frequency as time goes on, and this is sort of been called a sag trombone. It sounds like that when you make an audio representation, and so that's a common phrase that's used particularly by the observers. These things are very common, much more common as an observed phenomenon if you generalize to the whole sky. Instead of being about one per day, which is typical for a gamma ray burst, these work out to be about one per minute at 5. That should be 5, not 5 years, but 5 Jansky. Sorry, about 5 Jansky. So they're bright objects. They happen about one per day at 5 Janskys, and there are undoubtedly many more that are fainter and perhaps somewhat harder to see. Many thousands have been studied already, and it's clear that there are many more to come. And people talk about there being probably, well, many millions that can in principle be found by signal processing. Again, I'll return to that point in a moment. So these are the fast radio bursts and what characterizes them. Let's just go on. Do I have them? No, that's right, yeah. Okay, so I said that I mentioned propagation because what was found very early on was that because they are propagating through plasma, the group velocities of the low frequency waves are less than that of the high frequency waves, and so the pulses are themselves broadened. And this dispersion is easily removed. And so if we look over here, after removing the dispersion, we see that in addition, as you go to lower frequencies, the pulses get somewhat broader. And this is due to scattering, and this is an effect that is well known from the interplanetary medium and from the interstellar medium. And it's somewhat ironic that the instrument that was used to find pulsars was actually built to study interplanetary scintillation for X like this, but we're actually, what we're seeing here is the same sort of processes going on in the intergalactic medium, and on knowing the amount of dispersion there is, you can get the distances. This is working out very well, and they're typically gigaparsec distances. They're cosmological objects, and knowing the distances, you can figure out that the energies of the radio waves that are emitted, which are only about 10 to the 33 joules. It's not very much by cosmic standards. So the energies in an individual pulse are about 10 to the 33 joules. Some of these objects are repeaters. Some repeat very frequently. Some have been seen to repeat very often. Obviously, we're looking at observational cadences and trying to make some sense of this. It's possible that they all repeat. That can't really be ruled out. Obviously, it's very hard to rule out. But amongst the repeaters, there are identifications being made. And recently, one has been identified with MAD1, and there were reports of it being associated with a globular cluster. I'm not sure whether that really is held up. There's actually 2 or 3 now that have periods, one with a well-defined 16-day period, so it looks like it's in a binary system. Again, these are all clues of early days in the investigation, but there's a lot being discovered very fast. So there may be many types of source there. Now, when I said that the supernovae and the fast radio bursts were the physical mechanisms, it could be we're looking at a very disparate types of object that make up the full set of so-called fast radio bursts today. So we shouldn't just say there has to be one mechanism for everything, but that's the simplest way to start. Telescopes, radio telescopes, have been repurposed in Australia, in Canada, in the United States, in Europe, to look at these fast radio bursts. Here's the chime array, which was constructed basically to do hydrogen line cosmology, and in fact has the same facility, using the same data stream essentially, is being fabulous for exploring fast radio bursts and also pulsars and pulsar timing as well. There's a futuristic view of a facility that will be made fairly soon, and there's big plans to making special purpose observatories for looking at these and expanding on existing networks and so on. In terms of hardware, the effort doesn't really it's low frequency radio astronomy. The effort doesn't really have to go into the facility. It really, where the effort will go is into the computing and the signal processing and the electronics and so on. That's where the future lies in this business. But anyway, these are some of the observed properties. And as I emphasize, there's not a lot of power in them, and that's a sort of tribute to radio astronomy. I like to say that radio astronomers are very sensitive people, and so they can see very small amounts of power from the other side of the universe, whereas gamma ray astronomers, they need to be hit over the head with a source speaker before they can actually pick it up. So now there was possibly a breakthrough here, and this was a so-called soft gamma repeater, which is one of the three types of gamma ray burst, well known in our galaxy, and two facilities, one called Stair 2 and the other Chime, which I just showed you, and here are Sri Kulkarni and Vicky Caspi, who are the leaders respectively of those facilities, and they found a weak radio burst, something like 5 orders of magnitude weaker than the strongest radio burst, but it's in our galaxy, and it is identified with a soft gamma repeater. And so obviously when I was talking about magnetars and then talking about fast radio bursts, the connection is that most people now believe that most of their fast radio bursts, or the dominant class of fast radio bursts, are associated with magnetars. And I'll come to that point in a moment. This is sort of, don't worry about what all these acronyms are here. These are the fast radio bursts here. Here's a sort of measure of the energy, and here's SGR 935-215, and you can see the brightness temperatures and so on. And what happened about this one, it wasn't an exclusively radio object. It showed strong X-ray emission as well. That it was much more powerful than the radio emission that we're focused on here with the fast radio bursts. So, you shouldn't sign off on this and say it's clear that fast radio bursts are all associated with magnetars. But if, like me, you believe this from day one, you're very heavily encouraged by this discovery. And there's obviously more now. People know how to proceed. There's more coming, and in terms of these identifications. Something that's to me was very exciting. It didn't seem to make much of a splash, but and it's obviously again still early days, and I don't want to overstate what's been found, but it's evidence that in one of the repeaters, or three of them actually, but one in particular, there are evidence of constant periods being seen in the emission. And the period seems to be very well defined. It's about 200 milliseconds in this left-hand source here. And the speculation, which I think it was a bit too polite to make, but I think a speculation that many of us would make is that one is looking at some sort of surface mode in terms of the neutron star, and could be the dawn of nucleosseismology, and would tell us a lot about the equation of state of cold nuclear matter and much else besides that define neutron stars. So I think this is a very exciting prospect to watch this space. Maybe this will all go away or something, or it will be some sort of anomaly, but it looks pretty good. I think the fact that you start to see these periods associated with the emission. Very different from the so-called orbital period that's seen in the 16-day orbital period. So I sort of jumped the gun a bit and said that I personally think, and most other people, most of those now think, the theorists as well also think that now believe that they're magnetars, but that didn't stop them speculating, as happened with pulsars, little green men and all of that, as happened with fast radio bursts, where there were more theories out there than there were known objects at one point. Just to give you two aphorisms that encapsulate this, one by Kavli, who I just showed a picture of, said, when you've seen one fast radio burst, you've seen one fast radio burst, because they're such a heterogeneous class of objects. And Mal Ruderman, when confronted with this long list of published papers on explanations of gamma ray burst, said, I believe that every model ever proposed for a gamma ray burst is true for one object. So, just trying to be polite, I suppose. But the same thing happened with the fast radio bursts. Now, the two that are important are radio interference. Many of the objects that were thought to be fast radio bursts are just plain interference, and they were quickly filtered out. There was the embarrassing issue of an observatory that had a microwave oven. That really is embarrassing for a radio astronomer. They took out the ones at lunchtime. So they could figure that one out. And then we saw alien night sail strings, white holes, primordial black holes, entangled molecules, all of these things are there, strange stars, ball lightning. This is only a partial list. There's actually a collection of these. And the remarkable thing about these is that I think every one of them made them into a published paper. And so we don't, I think people aren't so deaf. Only one of these, I think, has had any duration. I won't identify it. The more astrophysical explanations that may well account, I think, for some of these bursts, but there's no strong reason for believing this, are active galactic nuclei. They could be associated with active nuclei. They could be one-off byproducts of supernova explosions. They could be byproducts of merging neutron stars as well, and also black hole binaries that have been suggested in this. And that may not be so crazy for reasons, but I don't really want to go down that road. The other possibility that I think, I'm going sort of in what I think is ascending order of credibility, the other possibility is that they are in fact, some of them are just pulsars, and the Crab pulsar famously occasionally produces so-called giant pulses, which are very intense flashes of radio emission. And so if the Crab pulsar were a lot further away, that is all we would see from it. And it's possible that these are some sort of scaled up version of the giant pulses from the Crab pulsar. So, so that may well account for us. But the smart money now really is on magnetars, accounting for most of them. And that's the context in which the rest of this talk will be continued. Okay, so I've done that one. That's right. Sorry. Okay. So what I'm going to talk now about is what I think many of the people who thought about magnetars, and as I say, there's a lot of literature out there on this now for the last 2 or 3 years, is that it's basically a magnetic flare associated with the surface of a neutron star. Remember, we're talking about 100 gigateslas here. So there's a lot of magnetic energy there, but it would scale maybe like the sun. And just like the sun, you can twist the magnetic field lines, drive currents along them, they can go unstable. That's one way, that's a sort of souped up solar flare, like that seen from the sun, but on much larger scales, of course, as a magnetic field. But also, what I think is now looking a better bet is that something happened beneath the surface of the star, it's a starquake. So there's lots of reasons why a young neutron star should release free energy, vortex line unpinning, and many other mechanisms that have been identified, which will allow an almost impulsive release of energy in the interior of the star, just like in an earthquake. And this would, and the fact that there's a period there, if there's a period there, then I think this gives credence to the fact that it's actually something beneath the surface rather than just instability above the surface in the magnetic field. So the idea is that you launch electromagnetic waves, and then if you say those electromagnetic waves that are launched by these relativistically rearranging magnetic field lines for whatever reason, those two reasons, they'll have electric fields in 10 teravolts per meter sort of scales, magnetic fields of about 30 kilotesla and so on. That will be the sort of typical magnetic amplitude. And under these conditions, the electric fields are so enormous that it is very easy using QED processes to make electrons and positrons. So all the small amount of charges you need to carry the electrical currents and so on is made instantly available. So there are many methods. These are two that are identified. Obviously, gamma plus a perpendicular component of magnetic field will make a pair, and a gamma ray, two gamma rays together can make a pair. And there are many other mechanisms. It is so easy under these enormous electric and electromagnetic fields to make pairs. And the plasma that you make is almost certainly dynamically quite unimportant. But the characteristic wavelength of the disturbance that you'll make is probably going to be in the kilometer scale. So most of the energy is going to go into kilometer scale waves, and that's the point to which I'll return. So you're going to make these sort of giant electromagnetic surges, and they are going to propagate out to the magnetosphere and somehow or other create a fast radio burst. That's the sort of generic explanation for what's going on. And I'll get a little bit more specialized down the road. So whimsically, I'll take the Aristotelian approach and say that these four processes here are something like an earthquake, something like a whip cracking, Indiana Jones and so on, with the whip cracks. It's a bit more complicated than this, but the popular thing in the set is that the end of the tip of the whip moves supersonically, and that's what makes the like that. And that's like the energy going down the magnetic gradient of the outer magnetosphere, becoming highly nonlinear at the end and moving essentially more and more power. So that's the sort of air, if you like. And then there are electrical disturbances, discharges going on there all the time. So that, if you like, is the fire. And then the final thing is the water. So this is the surge, and this is a tsunami, a dreadful thing that happens on the Earth. And I would like to make a point of physics here. I emphasize that the occupancies could be as high as 10 to the 40 and so on. If you ask about the corresponding occupancy looking at a quantum mechanical tsunami, it's about 10 to the 40 as well. And yet you don't see oceanographers talking about states or even water molecules and investigating their private lives and so on. They're dealing with continuum mechanics, they're dealing with a fluid, and that's the way they transact their business and tell people whether they're in a danger spot for a tsunami or not. Okay? So, and so that's generically true. Even if you go to a real trombone, I said the side trombone, if you go to a real trombone, I think the brightest temperature for a trombone is about 10 to the 20 or so. It's classical, it is, there's gas dynamics, it's aerodynamics. We don't get hung up on the quantum mechanical description, despite the fact that it's true, it's not useful. And I'm going to push that point further when we talk about the interpretation of this. Okay. So, if we talk about the models that are out there, and I want to be fair to my colleagues, they can sort of say, well, where does the radio emission come from? It's an issue of geography, if you like. And one class of models, which is the one that I favor, at any rate, is that it's very near the surface. The fast radio bursts originate close to the surface of the neutron star. Others, I think this is probably the major, I think it's, the other two are sort of more equally supported. One is it's in the outer magnetosphere, and it's a sort of variant, an important difference, but a variant on the mechanisms that I already identified for pulsars. There's the antenna mechanisms, which are the sort of giant electrons moving along curved field lines. There are the maser mechanisms, which I already mentioned, and again, these have enthusiastic proponents. And then these models can account for the components it's called and the polarization and so on, and they're tuned to do that. And then the third class of models is that as I said, also for the pulsars, there's wind emission, and these have enthusiastic adherence. There are other people who say that the emission comes from a shock front, essentially, that's propagating out through the wind, and current sheets in that shock front make the coherent radio emission. And it could be at distances as large as approaching a parsec or so away from the neutron star. That's what's claimed in those models. So these are, so there's a lot of uncertainty as to where the emission comes from, just like there's a lot of uncertainty about the mass of a dark matter particle, for example. And so there are many options out there. There have been many simulations that have done. This is on the, as Ewan did, of hydromagnetic waves going out into the outer magnetosphere. You can see that there, and how they would develop and so on. And I would say all of these, none of these can be ruled out as yet, but I am nonetheless going to talk about one particular class of models. And to do that, I'm going to segue into some electrodynamics at this point. And when talking about relativistic plasma physics, there are essentially 4 different ways one can think about this. One is one can think about it, as has been done in many circumstances, as essentially just vacuum electromagnetism with no currents and no charges, and or in the region you're interested in. And this would, for the Kerr-Newman geometry for charged black hole, for example, which is what you would do. The second approach that can be used to describe relativistic plasma, and this is the one that I will develop in a moment, albeit briefly, is that it is force-free electrodynamics. This has fields and charges, but nothing else. So I'll come to that in a moment. The next one that has been involved many of these codes is that it is relativistic magnetohydrodynamics. And this is in fact the union, if you like, of electromagnetism and fluid mechanics. And there's plasma that is present in serious density, that its inertia becomes important. It has a density, it has a pressure, it has a bulk velocity. In the most simple versions, there is no resistivity, no formal resistivity, but this can also be added. And this has been a lot of work done on relativistic MHD for these and many other applications. And there are very capable codes out there which can be employed to explore different versions of this general class of models. And then the final one is to treat the plasma not as a fluid, but as a kinetic substance with electrons and positrons, typically, and follow the motion of the individual particles within this, and then, as one does in body simulations and so on, average over volumes to get the current density and charge density and so on. And these are so-called, usually called PIC codes or particle in cell codes, and that they were invented in the 1960s, but they have been developed rapidly and very effectively for a wide class of relativistic plasma physics problems. And they can now incorporate general relativity, quantum electrodynamics, and other radiation processes and so on. And again, I'm not going to showcase those except to say that these are being used to do this. In order to run these codes, you have to put in artificialities, which is usually the mass ratio is not that, for when you've got protons involved, is not that normal 1836. And also you have Larmor radii, which have to be significant fraction of the scale of the system, rather than as would be typically the case here, something like about 10 to the minus 16 or so. The ratio of the Larmor radius to the size of the system in a neutron star would be tiny. And that I think that is important. Okay, let me go on. Okay, so I said I'd say more about force-free electrodynamics, which is the approach that I follow. And so there you see Maxwell's equations. And what you have here is, if you ask what the electromagnetic Maxwell's equations you know about, the electromagnetic force density is rho A plus J cross B. And that is considered, if you like, the divergence of a stress tensor for Maxwell. And it's interesting historically that, of course, Maxwell famously followed Faraday's researches and so on, and then sort of with after some thought and so on, wrote down his famous equations. And but in the treatise from the 1860s, he treats the electrical current as essentially as a fluid, as a continuous fluid. Now, I'm not a historian, and I don't know what said that and so on, but to me, it's almost inconceivable that the man who knew all about Faraday's laws of electrolysis and had contributed so much by that time to the kinetic theory of gases did not entertain the possibility that the carrier of charge, like the carrier of mass, was an atomic-like quantity. But nonetheless, the way he developed the electromagnetism was to treat the current as a continuous fluid. And you'll see a sort of the hobby horse that I have here, that we should perhaps do the same here. So if we do this, and obviously this implies immediately that there's no electric field along the magnetic field, that's a Lorentz invariant, also its gradient, seen in time and in space, is 0, 2, and you can use this to develop these equations. I won't give them all here. This is the current density, constitutive relation for the current density. It just depends on the electromagnetic field. It's a bit along the field and a bit perpendicular to the field, current density. And the point I would make is that the QED processes in these environments are so important and so strong that you can ignore them. All right? So what I'm saying is they happen so rapidly and so clearly that any charge that you need under almost any circumstance can be delivered. And so we don't have to worry about the private details of it. The QED, we trust it's there. The details, though, are unimportant here. They become important later. And so here's the final with his bongos, and on the back of a dollar bill it says in QED we trust. And so we trust that, and it will do its job and provide current just as we need it. And there's 10 zettavolts available, maybe. That's 10 to the 16 times the minimum potential difference needed to create the electron-positron pair. It's not that easy in practice, but it's not 10 to the 16 times more difficult. There will be a large multiplicity and so on. There's 100 examps here. For those of you who like CGS units, that's 10 to the 19 BO, which I think is the unit of current in CGS units. Not everybody knows that. So at any rate, this is just electrodynamics, no mention of matter or velocities of matter or anything like that. Now, if you ask what this means, there are two modes here. I'm going to call them the fast mode and the slow mode. The fast mode looks just like an electromagnetic wave with E equal to B, perpendicular to the direction like that. And then there's a slow mode, which is like an alphane wave, where the energy flows along the magnetic field, and E is perpendicular to the magnetic field. Those are the two polarizations. The characteristic information is carried in this way. You can make this more complicated by adding this resistivity, like viscosity and so on, but it shouldn't be necessary for reverse treatment. So if you think about what might happen following a magnetic disturbance on the surface, a giant magnetic flare, or more, I would say more likely now a star quake, there's going to be an F mode, which is going to expand more or less like a vacuum electromagnetic wave at the speed of light. And it's independent, and it's going to be independent of the magnetic field. It's just going to propagate radially, essentially, but it does matter that it's force-free because the polarization is adiabatically conserved along the ray. The S mode, however, carries energy along the field lines, as I said, like an alphane wave, and that leads to interesting effects. For example, if one imagines looking at one of these disturbances in the far field, one has to put in the retarded time effects, and you can build up very easily to show demonstrations of multiple imaging of caustics and so on in the wave propagation for these S modes. The S modes themselves, they do not steepen to break like a tsunami might, like an ocean wave might break. They don't steepen, but they do become nonlinear when it's typically at about 10 stellar radii. They'll become nonlinear, and so the amplitudes will be comparable with the background magnetic field at that point. And so about 100 kilometers or so will be that, and these are the characteristic amplitudes at that sort of radius for a typical wave of this type. Now, as I emphasized, these waves start off initially with characteristic wavelengths of order 100 kilometers. And what is interesting is if you take the view that force-free electrodynamics will work all the time, the rules that are in Maxwell's treatise, if you like, post-Maxwell and pre-J.J. Thomson electrodynamics, we are dealing with particles. Remember, we're just dealing with electromagnetic field and current. We haven't started atomic physics, nuclear physics, plasma physics, or particle physics. All of these, sort of reductionist views are not there. It's just continuum mechanics, like fluid mechanics. And so if you consider how the waves will interact, and so if you have more than one wave, then it is very easy to create a circumstance where two waves come together and will create a region which is called an electric zone, where the second Lorentz invariant E squared minus B squared becomes positive. And my contention is that even in that regime, a self-consistent description in this environment of the electromagnetism is just force-free electrodynamics, not the plasma physics, not the... So what we have then is we use those equations that I sort of sketched before, then we find that as soon as the electric field becomes greater than the magnetic field, a long wavelength disturbance becomes unstable to the production of shorter wavelength waves. And the contention is that those become the radio waves that are observed by radio astronomers in fast radio pulsars. And so there's a broadband radio wavelength turbulence. There's a lot more details to this. And so what we have is these force-free waves of much shorter wavelength, with meter and centimeter wavelength, say, going out into the magnetosphere. They're going to be completely nonlinear. The background field is very small by comparison, and eventually they'll come to a point where you can no longer make the charges and currents you need to carry these waves through. The fast modes are essentially electromagnetic anyway, there's no problem with them. The slow modes do require a mode conversion to an electromagnetic wave. And I actually think this can happen with high efficiency. Others doubt that, but at any rate, this is the mode conversion to an electromagnetic wave, and that will typically happen way out in the outer magnetosphere. So what starts off as one of these force-free waves, if you like, then becomes essentially an electromagnetic wave, and is there, propagates across the universe for the gratification of radio astronomers. So that's the base. I'm just sketching this here. Obviously a bit more to it than that. So for this particular model, there are some issues. And I think these are things that are certainly worth thinking about. One is, do you make the F waves, the fast modes, in a flare or a quake? Some people think you only make alphane waves. Again, I'm very suspicious of that. I think you make both types of wave. The second one that I've already emphasized is, does the electromagnetism follow the force-free prescription when E is greater than B? My contention is yes, but it's not demonstrated. Probably fixed simulations and so on will be needed here. There is, because you've got waves made on a range of scales, there's an inner scale, just like there is, say, with the Kolmogorov spectrum, there's going to be an inner scale where dissipation happens. What's the influence of that? I think it's unimportant, but it needs more examination. There's an issue whether the radio waves can escape from the inner magnetosphere. Many people think you can't get any radio waves out from the inner magnetosphere. I would dispute that, but that's worth more examination. Does the magnetosphere allow even S waves to escape? I've said that I think it does, but again, it needs more calculation. And then what are the sort of making more contact with the spectrum and polarization and so on for the observations? There's much more you can do there. Is this approach of any use in trying to explain the emission from pulsars? I thought less about this personally. I thought less about this, but there are ways in which this could be of interest in that context. In the pulsar magnetosphere, you have very modest voltages, particularly the slower pulsars, and modest currents, and it's a bit of a struggle to make the quantum electrodynamics work. And it's probably going to be more like terrestrial lightning, where the charged cumulus cloud and having charges, having lightning strokes and so on. And then the electromagnetic disturbance becomes a sort of thunder. And again, if that's the case, those waves can locally easily get into a regime where E is greater than B and can make centimeter and meter radio waves. And this would say that the radio emission originates from very close to the surface of the neutron star. And there are reasons for being a little bit suspicious about that, but I wouldn't rule it out. So I'm less sure about where this is going for the pulsar emission, but it's certainly an interesting possibility. I'd just like to conclude with one slide, and that is the cosmological promise here. I said I would say a tiny bit about cosmology. Remember, CHIME was built for doing cosmology. It's very hard to do cosmology with it, but they will succeed, I'm sure, eventually. But ironically, this stellar telescope and others like it may give lots of, may teach us some cosmology. And here are some of the possibilities. If millions of these objects are catalogued and seen, and this is an issue probably more of signal processing and data analysis than it is of radio telescopes, then you've certainly got a very large N. You can investigate directly the distribution for the dispersion of the intergalactic gas, and that has already been quite a lot of work done about that. I'm not going to repeat it here. One can learn about the intergalactic magnetic field and so on. Gravitation, there's going to be lots of gravitational lenses here. Those who believe that gravitational lenses can give you the Hubble constant might be encouraged by this, because the possibility of doing this, although I, as I said to the students, and I said last time I gave a talk here, I think it's going to be a tough job to beat the wonderful work and analysis that's been done by George and his colleagues with Planck. And then there's probes of galactic structure and large-scale structure and so on. Again, we don't quite know where this is leading, but there are certainly possibilities that this, like the pulsars themselves, will turn out to be wonderful tools independent of how they actually work. So let me just finish at that point with a summary, and thank you very much for the invitation to give this Kavli lecture.
Thanks very much indeed, Roger, for a fascinating talk.